In our last video, we stopped just before we got to number 74. Well, what I realized was number 74 that was printed in the older version of the textbook that I was using is actually a little different than what you had. So I printed it out and took the time to make it a little larger so it'll show up better in the video. But this is problem number 74 off of page 352 in your textbook. And what we have here is some information about the world tiger population. We have a bar graph that estimates the tiger population based on data. It's alarming. And then we have a polynomial model, which I've written here. The x's in the polynomial model are years after 1970, and the y's are the world tiger population. So I'm asked to find and interpret f of 45. So let's start off by finding f of 45. So I have 0.46 times 45 raised to the third power minus 14 times 45 raised to the second power minus 1079 times 45 plus 37,979. And we get 2,992 rounded to the nearest whole number as we were instructed to do in the problem. All right, so that's not the interesting part. Now the interesting part is to interpret it. Well, the x's are years since 1970. So 45 years after 1970 would be the year 2015. Not too terribly long ago. So this model predicts that there were 2,992 tigers in 2015. Part B asks us, does the rounded f of 45 overestimate or underestimate the actual data shown in the bar graph? Well, in 2015, there were 3,062 tigers, so we underestimate just a little bit. But it's a good estimate. We're not too far off of that 3,062. Part C, use the leading coefficient test to determine the end behavior to the right for the graph of f. Might this function be useful in modeling world tiger population if conservation efforts to save wild tigers are successful? All right, well, looking at the polynomial, the degree is 3. And the leading coefficient is 0.46, a positive value, so the end behavior would be falls left, rises right. Well, in the short run, since we're rising right and we want to see these bar graphs go the other way, this could be a useful model if conservation efforts are successful, because we're rising to the right. If the conservation efforts are successful, then we should see the population increase. That being said, you should always be wary of polynomial models for things like populations. Populations cannot rise unbounded forever, so it would always be a model that would help you, but not too far away from the scope of the original data. Eventually, even with the best efforts, we will see a population level off towards its carrying capacity. Populations can't grow unbounded forever, but in the short run, if we're going to see these conservation efforts be successful, this does appear like it's a good model.